Hi, welcome to another video from Singularity Engineering. My name is Jesus Ramirez, and I'm going to talk to you today about the evaporation model in ANSYS Fluent. I hope you enjoyed this video and learned a lot. Remember, we are Singularity Engineering. ANSYS Fluent uses one of two models for interface mass transfer through evaporation condensation. With the BOF and mixture formulations, the Lee model is used. With the Lyrian formulation, you can choose between the Lee model and the thermal phase change model. In this video, I'm going to explain a case by using the BOF formulation. For instance, the Lee model is going to be used. The geometry is composed by two zones. The red zone is the region where the coil is located, and the blue zone is the region where the cold liquid is located. For instance, the blue zone is the region where the liquid vapor phase change will take place. The red zone represents the region where the hot fluid flows through. This flow will provide heat to the liquid located at the blue zone. The heat transfer takes place from the red zone fluid through the wall by convection, then the heat goes through the wall by conduction and is received by the red zone fluid by convection. Then, through this heat transfer process, the evaporation phenomenon is going to be placed and a phase change is going to be noted into the simulation. In the meshing process, a very standard mesh was used. Particularly, inflations were prescribed at the walls in order to obtain a better prediction of the boundary layer. Also, body sizings were used in order to improve the accuracy of the model. Also, different name installations were prescribed. We have an inlet and an outlet into the coil. We have also an inlet and an outlet into the external part. We have the walls of the evaporator that are isolated. We have here this wall, which is the one where the heat transfer process is going to be performed. And this wall here is going to be isolated. Once the mesh was performed, the mesh looks like this. As you can see here the inflations in order to consider the boundary layer effect. And this is the mesh we are going to use in this video to show the setup of the evaporation model and to show you the results we obtain with this model. Once you have performed the mesh, you open the Fluent setup, you load the mesh and you check it. Everything is okay. Then I'm going to use the transient formulation, a pressure-based solver. I'm going to use the gravity in the negative direction of the y coordinate. As I am going to enable the multiphase model. Then, as I told you earlier, I am going to use the volume of fluid model. I am going to use 4 Lyrian phases. The I am going to use the explicit formulation because it's more accurate and it is possible because the transient formulation of the temporal advance. I also am going to check the implicit body force. I want to resolve the interface, the freezer phase in the evaporator. Then I am going to use the sharp interface modeling. You can see that the phases I have already loaded. Then I have the primary phase is the cold liquid, that is the one that is going to be here, which is going to form the freezer phase. And the secondary phases are the gas that is formed by the evaporation process, the hot liquid that is the one that is flowing into the coil, and the air that is initially in the upper part of the evaporator before the evaporation began. Then once the evaporation began, the vapor is going to be flowing here and the air should be going outside of the evaporator through this pipe. Okay. In phase interaction, in the force, I'm going to use the surface tension coefficient as a constant. Then you should do a research in order to find the, the correct value for the surface tension. Okay, it depends on the material you are using in your simulation. And in heat and mass and reactions, I'm going to use a one mass transfer mechanism, the evaporation condensation model among the cold liquid and the gas. These are the materials or the phases that are going to be evaporated. Okay, then as you can see here, the only option we have for the evaporation and condensation model is the Lee one, because the BOF formulation that I am using in this simulation, these values I will let them by default. And here is the saturation temperature of the cold liquid. In this case is 77.364 Kelvin. Okay, once you have do that, then you click apply. I have already done it, and I have load all my information. I have enabled also the energy equation because we have heat transfer processes, and I'm going to use the K omega SST viscous model because it is recommended for heat transfer processes in order to model with more accuracy the boundary layer. Well, once we have defined the setup of the multi-phase model, we have to go to see the cell zones. You can see here that I have um, built two cell zones. The first one is the external part of the evaporator, and this one is the internal part of the coil. Okay, then I'm going to display all of them. Okay, then as you can see here, if I double click here, you see that the cell zones are prescribed as mixture. That is correct because the multi-phase model we are using. Okay, we have also a solid zone, that is the wall. This wall, that's where the heat transfer is going to be going through. So I display it. You see here, this is the wall. Okay, I'm going to display. Okay, well, we have the cell zones, and now we are going to define the boundary conditions. Then in this case, initially I'm going only to enter fluid through the coil. I'm not going to use this one. This is just for simplicity, for explaining the model. If you want, you can after that after this you can do the simulation and prescribe the boundary conditions, the inlet boundary condition here. Okay. Well, then the inlet is here is hot liquid. Then for me this is a velocity inlet 0.1 meter per second, and that is entering at 79.3 Kelvin. Okay, then now I have to define which phase is going to be entering here. Then as you can see here, then I have to do nothing for the cold liquid. In gas, the volume fraction is 0, no blast is entering. The hot liquid is 1, that's correct. And here for the air should be 0, that's okay. The sum of the volume fractions should be 1. Okay, then only hot liquid is entering through this pipe, is entering to the coil. Okay, then we have here a pressure outlet. Then for me the pressure outlet is to atmospheric pressure. Then I double click. I have two pressure outlets, sorry. This one and this one. This one is the outlet of the coil, and this one is the outlet for the evaporator. Then all both of them are pressure outlets to ambient pressure. Then you see here a zero gauge pressure and a backflow total temperature of 77.3 in this case. Okay, and in this case we have a 77.8 backflow because it is difficult that the exit temperature should be the same of this. Then that's the reason this is a higher temperature, backflow temperature, uh, when it's comparing to this one. Okay, then also if you see, I have a backflow volume fraction here of 1 for the hot liquid. That's because there is only hot liquid here, and here in the other part I have a backflow volume fraction of 1 for the vapor, because at the end this should be all filled by vapor. Okay, that's the reason. For the walls, then you can see here that I have different walls. Okay, then for example, this wall is this one that is isolated, and if you double click, you will see that the thermal option heat flux 0 because it's isolated. Okay, then we have this part here, this inlet, that in this case, or for simplicity, we are not going to use it. Then this is a wall, you can see it here. Okay, then that's also prescribed like as a isolate. Okay, but for example, you have here, let's say this one, this one. Okay, this one is the back part of the coil. And as you can see here, this also is resolved like a coupled one, because from that from that um, wall is going to be heat transfer. Okay, then also you see in this case the 12 volt isolate is the part of the coil that is going to be isolated, and you just can see it. If you double click, then you will see that the heat flow is 0. Okay, and this part here, for example, is the other part of the coil that is in contact with the fluid, and it also is a coupled formulation. Okay, then it is very nice. In this case, I am using the thin wall model. Then I am just modeling the wall width by doing the geometry, as we already saw in the in the previous minutes of this presentation. Okay, then we have already defined the boundary condition. Now we have to move into the methods. Then I'm going to use the couple scheme with the press to approach for the pressure special discretization. I'm going to use the bound security implicit. It's more accurate in these cases, and I will leave this one as this. Okay, then we have to initialize. For that, we need firstly to create some cell registers. Let me show all the mesh. Okay, we have to register some cells. I'm going to delete this one. Okay, I'm going to create it again. Then I'm going to create a region in order to have the cold liquid here initially with the freezer phase. Then let's say it's -2, 2, minus, let's say, -1, 0.3, and save and display. Yes, as you can see here that these cells are going to form a region which I'm going to patch with cold liquid in the initialization process. Okay, then I save it, and okay. Now I'm going to initialize. Initially, I'm going to use all zones, and for me, everything is going to be filled with air. Okay, now everything is filled by air. Let's see if that's true. Then volume fraction air. Okay, then we have here the phases, here volume fraction, and you can see that everything is filled by air. Okay, then now I'm going to patch some of this. Then I'm going to select the region. Okay, then I'm going to use this one, like for me is called liquid, that is the primary phase. Then for me this is going to be a volume fraction of 0. Okay, then I'm going to patch it. Okay, and let's see another contour. This is volume fraction of cold liquid. Yep, quiet, and we can see here that we have here air, that is the phase that was before patching the cold liquid, and here all of this is cold liquid. But in this case I have two options: to fill this with hot liquid from the beginning, on to let like this and enter in the hot liquid by boundary condition, and in the transient formulation see how this is moving. For for visualization, it is nice to see how the hot liquid is entering, but it is too time consumption for the simulation. Then I'm going to patch this as hot liquid, everything in the inside the coil. Okay. Then if you don't remember how the coil is name, remember that you have this fluids on, then remember you can go here, display, and the contact region target is the one that is the fluid inside the coil, okay? And let me again display everything. And you go again to initialization, patch. Now you have to use this one, okay? Contact region, target, then hot liquid, volume fraction of 1, you have to patch it. And let's see if that's true. And new volume fraction of hot liquid. This is hot liquid here and displayed. And there is something weird here. Let's check what happened, because everything here was like moved with. Let's check. And I went back. Okay, that's a reason. Let me select here. I have selected the region. Then for me this is only, this should be like volume fraction 0. Okay. Then if that's true, then this should be okay. Perfect. This is air. This is cold liquid. And now I want to fill the coil with hot liquid. Then I have to select this one. Deselect it. Okay. And now put the volume fraction here for this one. Okay. And hot liquid. That's it. Then I have air, cold liquid, and hot liquid here. I have initialized correctly my simulation. Um, you can see here that there is something that we did wrong, but maybe it allows us to begin well. Okay, then let's do it again, because I initialized everything like 79.3, and that's not correct, because the saturation temperature of the cold liquid is 77.3. Okay, then I'm going to put this 77.3. Okay, all zones are going to be initialized with air. Okay, then 77.3, have this value here. Then I'm going to initialize. Okay, that's correct. Then I'm going to patch. Okay, this one. This is going to be only water. Then for me, this patch 0. Okay, and this is going to be hot liquid, volume fraction of 1. Okay, that's correct. And the mixture in the hot water, yeah, should be a temperature 79.3. That is the temperature that the hot liquid is entering into the coil. Okay, then let's see. That's correct. That's correct here. And if we see of air, that's correct. Okay, then finally, let's see a profile of temperature. Okay, and we see that everything is at 77.3 Kelvin, but the fluid inside the coil, that is at 79.3. Then at this moment the initialization is correct, and we can start our simulation. I'm going to run this. I I'm going to run the simulation. We can check here. No recommendation at this time. And once it finished, I will show you the results. Before running the case, it's important to remark that the time step can be performed by using the fixed or the adaptive method. Okay, then I'm going to use initially the adaptive formulation because I don't know which could be the adequate time step in order to have accuracy and not too high time consumption of simulation. Then you can change the time step or convert the time step by changing the global current number. That is the value of one is recommended, but you can change it, and sometimes you can use higher values, inclusive for 30 or 50. It depends on your simulation and how smooth are your conversions. Then at this moment, I just going to try a value of, let's say, 50. But if you see that the convergences and the residuals behave too bad, then you have to to put lower values of current number in order to have a better accuracy and a better stability of the method. Okay. Then right now I'm going to run the simulation, and once I have the results, I'm going to show you. Once the simulation has ended, we have this kind of results. It is important to remark that I have to change the time step by changing the current number. I used a current number of 2 in order to obtain a more stable solution. Then you can see here that the formation of vapor by evaporation. I am going to show you a few time steps. If you want, you can reply this tutorial and do all the simulation and all the times to see how this level is going to be reduced by the evaporation phenomenon. Then you can see that the vapor formation is more pronounced in this side than in this side. The reason is the hot liquid is entering through this part into the coil, then here is hot, but when it's flowing, the temperature is reducing, and here the temperature is lower than here. Then that's the reason that the evaporation process is more pronounced in this part of the evaporator. I got a video, a very simple video to show you the time step I resolved and how the evaporation models worked. You can try to reply this tutorial. You can try to improve the model. Remember, this is just a demonstration. Then you could use a smaller cell size in order to capture or to be more accurate in the resolution of the model. Also, you can run more time steps in order to see the whole phenomena on how this level, the free surface is reduced. Okay, then right now I'm going to show you the video I got. Well, here is a short video showing showing you the how the process of evaporation is modeled by the simulation. Okay, then you can see here how the vapor is more pronounced here than in this region for the temperature distribution over the coil that I explained a few minutes ago. Okay, well, you can see the evaporation model is working. Of course, if you want more accuracy, you have to refine the mesh and and validate your model. Okay, this is just a demonstration to show you how to use the evaporation model in a very simple case. Well, it was a pleasure for me to be here with you to explaining this model. And as always, if you have any question, please let us a comment or visit our website or give us a phone call. Remember, this was Jesus Ramirez from Singularity Engineering. Here is our website. and this is our phone. Then if you have any question, please let us know. Remember, we are here to help you. We are Singularity Engineering. Bye bye.